Fan. Hey, it's working. Okay. All right. So last time we were working on BJTs. Just out of curiosity, what is a BJT? Just as a quick reminder to ourselves. Anybody even know what BJT means? So it's dealing with the fact that we've got those two different junctions that are in there. Okay. If you want to say characteristically, like what is a BJT? As far as transistors, right? Because there's categories of transistors. Um, what? How would you describe a BJT? Two diodes and okay, so two diodes and 10. How do you, like all transistors work, but there's kind of like a control segment, and then there's that amplified side, like the trans resistance side. How do you control it, the actual opening or closing, right, of the other side? What is it you have to do in order to make a transistor work, turn it on or off? You have to provide voltage to the base. So I have to provide voltage to the base, and what does that do? It opens up the path for the indicators. Okay, how? I agree with you. We're just digging a little deeper. Yeah. So it removes the depletion layer. Okay, so it takes out that depletion layer, right? Because we've done the voltage, we've handled, in essence, we had that. The depletion layer creates its own little bias that opposes this, right? You remove it, and then what happens after I go past? Get to the point, just remove the depletion loop, no more. And I just push past it. Then it's all. Okay. That's collector to emitter. Okay. And it's the way that works is I'm getting a lot of current flow, right? Over the current between my, coming into that base, right? So as I increase the voltage above the minimum to remove the depletion, we've now got carriers that are up in the conduction band. Remember, electrons are really light, so you apply a small amount of voltage and they go flying, right? So that's why you get that real sudden updraft once you pass that 0.7 minimum voltage to a burst, that band gap is. So in essence, what you're getting is whatever the current that you've got coming into the base, right, is going to become multiplied on the other side. You lower the resistance and you get a big current flow. Right? Even though you're applying voltages, everything in terms of a working function has to do with the flow of charges. Right? The way you remove the depletion zone is you're adding charges in. You're doing this by putting a voltage on them to shove them in, but you're adding charges to it. BJTs are thus called current control devices. Right? This is actually a really important concept, right? BJTs need current to flow. Now, let me ask you, the second current flows, and we said we've applied a voltage to it. What happens when you have voltage and current? Power. Voltage times current gives you power. And power in our devices, whenever we're here, we're sending power. What do you think of a device? Heat. Do we like heat? Do we like power use? Power. This is the big problem with the BJT. Because they are current controlled devices, I have to apply a certain amount of voltage. I need that to be able to break that gap. And in order to get things going inside, I need a decent amount of current. So there is a minimum power you can hit. They have power-hungry devices. If that's what you want, it's a lovely thing. Right? They tend to be static insensitive and all kinds of other stuff. But they are power hungry because they are current controlled. And we don't like that. The more current that's flowing, I need bigger wires, I need more heat dissipation, you can start adding this up. None of these are conducive to designing a really good digital circuit. This is why BJTs are becoming less and less popular. That is really the whole reason. It's the basic operation. So now we want to figure out how can we remove this need. You can't get rid of voltage, right? All of these are going to need that band gap to get rid of it. But what we need is something that's not going to have a large current flow. Because if we can knock the current out, then we can drastically reduce the power consumption. Does that make sense? So we need something that's not a current control device. We need something that's a voltage control. And voltage is the field. So we're going to want a field effect transistor. And here's one side effect. Okay. So I want you to understand, right? These are why they come in. This is where the names come in. And it has to completely do by our needs. If I was trying to switch a lot of current, I probably wouldn't care. Right? But I have no choice in this particular case. Okay. Let's start doing stuff then. We'll find out what color I grabbed. So now we don't like current. So the idea is we need to reduce current, right, for the purpose of reducing power. That's our goal. Now, if we think about the device we have built so far, in simple terms, we have something that looks like this, right? Let's say, for instance, like an NPN. And we have put in wires here, and we have a wire that's coming into P. But it's exactly that current that's coming into P that we want to get rid of. Right? So what I need to do is to block that current. So let me consider a first thing. What if I came in and I put an insulator here? I just blocked with it, right? So now you can't flow a current. Right? I mean, it's a big problem, doesn't it? It takes care of the problem of the current problem, but how we develop solutions. Yeah, so this creates the second half of that problem. I now no longer the way to really control that gate easily. But I'd like to be able to control it by a field. Is there a way that I can use an electric field and apply a field into here to try to remove it? Using the insulator just to prevent current flow. Do we have a device that uses an insulator to separate two wires in a circuit, but still allows a field effect to go? That's a capacitor, isn't it? So what if I just take here and now I put another layer on top that's just pure conductor? So now I have a field I can send across here. Right? And let's say, for instance, that I hook this up so that, I've got this to the, power. So let's say I hook it to like 5 volts. And what's going to happen? DC and just let it come through this DC. Will have a flow from the plate to positive. At least for a brief instance, I'll get a little bit of flow, right? What am I doing to that top plate there? You are exciting. I am, and I'm charging it up, right? So we talked about charging up that thing. What's going to go on that? Positive or negative charge? We have holes on one side.
negative.
So just think what 5 volts is, right? If I have high voltage, 5 volts compared to 0 volts, right? The other side's going to be relatively, let's just say it's wrong. How do electrons flow versus holes? We'll just use those as generic terms.
5 volts, or the low voltage is going to be a flow of electrons that's charged.
Yes. So what does it flow from? Does it flow from the 0 to 5 volts? Is that the way electrons go, or do electrons go from 5 volts to 0?
5 volts goes to 0.
So you seem to have a mixed vote here, right? How many votes electrons like to go from 5 volts to 0 volts? You can do it with love if you don't want. I don't care. But you gotta vote for one of these. I don't care which it is. Right? Or you just force your career reaction. You can't. You have thumbs up means it's gonna flow. It's gonna flow from 0 to 5, and thumbs down means it's flowing down and it's going from 5 to 0. Which way do electrons want to go? So they want to go 5 to 0, 0 to 5.
0 to 5.
Okay, so now everybody is giving me the thumbs up. That's good because that's what happens, right? So that 5 volts, it's going to be pulling those electrons in. Okay, so if the electrons are going up to 5 volts, what's happening to that plate?
If they're flowing toward the 5 volts, that means the plate is getting holes. So that means it has a hole.
It's getting positively charged. Completely correct. Right? So just remember, where the electrons want to go, and since they're moving away, you're left with the other charge. So that means this plate here, in essence, becomes positive. So we fill it all up. If it's positive, right, it's going to be field. And what gets attracted to positives? Negatives. So what's going to happen on the other side of my insulator?
So essentially, negative carriers flowing into the holes.
But they can't flow. The insulator prevents them from moving. I know. But this is actually what's kind of cool about this. This works a little bit different. Right? So they can't move anymore, so they're going to build up. So effectively, what do you have? You have a whole bunch of negatives. And what are those? Charge carriers. So the dominant charge carrier in that area is electron. We just turned a little thin layer into an N-type.
And so
We induced it, right? So you would have now a little tiny layer of N-type.
So now we have end to end.
Exactly. You built a line. Right? And so it's all N all the way across. So what's going to happen? Is that going to flow well? Oh, it's going to flow great. But how much current did it take? Almost nothing. It's a field effect, not a result of current. That's what's so cool about this. So we're actually not getting rid of the completions of the data. We're literally building the conductor where we want it. It opens it up, you've now turned the switch. And think about it, it's voltage, but the current isn't flowing, so what's the power look like? Very low, exactly. Right? And since the power is very low, what else is low? Heat, right? And heat is our big enemy. Right? Inside, so I keep saying heat's our big enemy. Let me ask, why is heat our big enemy?
Just increase the energy level of the electron. It could just jump over
Yeah.
the
That's what, so it requires, I mean, as I do this, right, I adjust things and it's gonna become in essence, more issue on those. But there's even a bigger one. There is like a deadly stop. So I agree, that's true. It's gonna raise that up and cause issues. There's like, but there is a game stopper in this one with heat.
induced mechanical.
So it will induce problems and failure and all kinds of stuff, and that stinks. But that problem does not grow exponentially till it kills us. This is what's kind of weird. Think about it. As I start getting smaller and smaller, in a smaller and smaller volume, I'm putting more and more transistors, right? So how are the transistors growing by the volume of silicon I have available?
Exponentially as they get small.
Yeah. In particular, it'll actually grow cubic, right? What's the volume? Right? So it's going to grow cubic. To remove heat, it has to leave the volume. So it means it has to go through the surface. And how does the surface grow? Less air. So as you get better and better at building things, the heat grows cubic, and the removal of heat grows squared. See the problem? This is why I think it's a game ender. Anybody ever noticed that in pretty much your lifetime, the speed of a computer hasn't changed? We hit mid 3 gigahertz in like 2003. Okay? And still, why?
Because of the heat block.
The heat problem. That's the limit of air cooling. As fast as we can remove the heat off the surface.
This is why supercomputers, I believe, use like liquid cooling.
Yeah, so that's why if you go to the brick, we actually have a cluster we call polar bear, which is immersed in liquid. So we can speed that one up to 4.5, 5 gigahertz. So when you start hitting the liquid cooling, right, we just submerge it in non-conductive oil and we super chill it. It's actually even cheaper to do that. So it's more efficient because you're concentrating it and you get a better transfer. So it's all a better thing. It's not universally used because companies like NVIDIA won't certify their stuff first. So there are some disadvantages that go on. As time goes on, they'll have to.
The next frontier, like improving transistors, would be how can we control the efficiency, how can we get to keep it higher and higher.
So this gets into, so we want more efficiency. So one of these areas is can we move to like single transistor, can we get real low power ones, things of that sort. That has its own areas. This is why in amongst the other problems that are there, this one is one of those killer problems for design and stuff. Right? This is why you have to switch to parallel. Now you can distribute your heat sources spatially out. You can spread them. Right? You can get it in different areas of the chip and monitor the temperature until things on and off as you need to maintain your heat properties. And, but this has been the game. Up until 2003, the game was make it go smaller, faster, that's better. Once you hit that limit, then you just couldn't cool it anymore. Now all of a sudden, this is why multi-core, all the parallel ideas, everything else starts taking over. Because you can't win this game. And it's just impossible. As you build it better, heat's growing cubically, and temperature removal is only growing squared. At a certain point, you're gonna lose. We've already crossed that. So now it's all about mitigating. So it's important to understand why. And this is part of why. Now there's a lot of other areas where this same thing applies to, right? Computation is similar to what you have with power generation or power usage. So if I build more and more structures inside the computer, my available volume to build those is cubic. But think about now your data flow. How do I get data in and out of the computer? Through the service.
To the heat, could you is there a way to increase the surface area such that it's larger than the volume?
So now you get into some fun things. This is where you start getting into like FinFETs and stuff like that, where you're trying to increase the surface area. So that's another direction you can go to. You're exactly right. So that's one of the areas. So people try to make these bins. to help pull the heat out so you can get a higher surface area proportional to your volume. Why do you do that? Because if you don't, you're in deep trouble. So my point is when you understand the underlying problem, you can start doing exactly that. You can start thinking, how do I adapt? If you don't understand the problem, you have no idea where to go. So that's why I wanted, as we're going into this, part of the reason why we want to discuss all this is because these are fundamental problems in the discipline. And how you solve them is going to be really important. I could also, for instance, increase whatever the thermal conduction is of, for instance, my base layer. So, people have played with things. This is why sometimes people talk about fiber or even diamond as the bottom for a chip, because they have really good thermal conduction. So people will play with all kinds, right? Just put a monolayer, right? You can create a monolayer of diamond or carbon fiber or things. Really good, thermal properties. Maybe I can just pull the heat out quicker, right? And it might give me a 2 or 3 times advantage in what I can stick in there. And while that doesn't solve the overall problem, it makes me better than my competitors. Right? Much like the FinFETs and everything else. They're all little games. How do I nibble at the edges to be able to do it? Right? So, I just want it floating in your head, right? These are those kind of big problems. And we see one way to handle it, we do exactly this. Now again, I need to be able to build this. So let's talk really briefly about how we build this. How do we build an insulator? All right, we're limited on what we can put in here because we don't want to cause some type of a weird pollution that ruins our semiconductor, right? So there's only so many, atoms we can safely use, right? That first top layer, right? A little bit on each of the edges, but essentially that's it.
Could we not use the same to positively negative targets? We use a chemical operation.
So that's exactly what we're gonna have to do, right? But we now have to think, like most insulators, right? We have special materials that we do as insulators. You can't do a lot of those, right? Because you just can't use their particular atoms. But have any of you ever tried to, or had your car not start and you think the battery's dead and you open it, pull up the hood and you look inside and your battery terminal's all corroded? Anybody ever, maybe you're gonna try it from slide or something that doesn't work? You know,
Like,
well, in a way, right? If you clean the corrosion, does the battery start working again? Yeah. So corrosion is an insulator. What is corrosion?
oxidative.
Exactly. Can we create a thin oxide layer?
Yeah.
That's any kind of semi-metal. So there's, aluminum oxide, there's iron oxide, there's also silicon dioxide. So on silicon, I can oxidize a layer. And silicon dioxide is a great insulator because it's an oxide, right? You already have that experience, right? Titanium dioxide, another really good one we will sometimes use after these. There are great, oxide layers out there that we can do. It's based on the same material we're dealing with. No questions here. So in essence, what we want to do is to make these specs, we want to make a layer of some metal oxide. We can do that. We've already taken, we can make masks, so we can etch them. So we can oxidize just in that area and let the protective mask handle it. And you can build a layer of metal oxide on your semiconductor. Metal oxide semiconductors. MOS. That's where that name comes from. A MOSFET is a MOSFET because you're going to make your insulator that separates this from a metal oxide. It is, exactly. But we have to be careful because we have to build it out of stuff that won't damage your semiconductor. So the names are actually really descriptive of the formation process. So if you think about now, that same process we were talking about, put down a link, some type of resist, alter it, remove the stuff you don't want to do your operation, right? Remove the unnecessary bits of the area, and now you've got your layer built in. And I can do this all across the entire semiconductor circuit. So I can do, thousands, millions of these little transistor oxide layers at the same time. Right?
And
So,
because they're never papers.
exactly.
Never papers, you pick
So I just cover the whole thing, photo the whole thing, right, to photoresist it, right? And I can just go through this process. It may be a bunch of steps to do one thing, but I'm doing millions simultaneously. So it's still overall pretty efficient. So you have to do 100 steps or something to chip. I might have just built 100 chips. So overall, still a good situation.
There's a transistor, basically, the brains of here, this forward to crisis, it's just on chip, but it's how we build them, this
Exactly.
project.
Yeah. So hopefully when you're seeing these, and part of the reason why I wanted to talk about these is I wanted to get you to think about how they have to be built. Right? Now, do you think when this process is going on, you might accidentally have some problem that creeps into your chip?
Yes, there's always going to be a error.
There's always, right? And this is when your chip failure rate, this is why you have to, be able to check it. What happens if like some little particle of dust comes in and lands? Think that could screw this process up? Yeah, absolutely. So that's why you have to make these in clean rooms, yeah, right? So you can see all the areas. As you start thinking about the process, you can exactly see why it has to be built, how it has to be built.
And also this difference to why more, they really want these is less expensive because you build one of them, it's tiny.
Exactly. And the smaller you make it, the more likely that, like, if I have one big giant chip that does everything on the wafer, right? I get a dust particle or two falls on that, it kills the chip. If in that same wafer you make 100 little chips and the same 2 or 3 dust particles fall in, I throw those 2 or 3 chips out, all the rest of them are still good. Fine. So basic economies of this is why doing smaller stuff is, again, beyond just the heat problem. It's also more likely to have a successful build. Good? Okay. So at this point, hopefully you've got the basics you need to understand these. Do you think I could do the same thing with a PNP?
Yeah.
Right?
It's the idea of the place the inverter.
Right? Well, I'm still going to have these. I'm going to still want my insulator coming through. I'm still going to build up my capacitor top area, right? But in this case, what do I want down here? Yeah, I want a positive charge, a P channel, right? So we call these the wire here, we call it channels.
So
Exactly, because so I want minuses here, right? And minuses come from the ground. Right? So you can figure out everything you need to figure out on it, and that gives me that channel. What if I want to turn this on? And if I want to turn the other one, does it immediately turn on?
no, the charge is paid.
Yes, so it's capacitor, so you have to discharge.
Your charge just as cause latency.
Exactly.
And so
So there's going to be a little switching time involved in this. And
so a BJT is faster, create a MOSFET.
yeah, so a BJT in theory can be faster. Right? Okay, so here's the thing. Imagine that, why don't you let me ask you this. What was the first power to a car that was ever invented? in the early 1800s, the first type of car was batteries. Electric vehicles were the first cars. It was too expensive and everything else to build them. So the less reliable gas engine was used. Now, after 80 years of development, how reliable did gas engines become? So it's pretty darn reliable, didn't they? Because they had a lot of things on it. Now we're starting to not like the effects of gasoline engines. We're starting to go back to older technology. But as soon as you think that technology is not useful, that will bite you in the butt, right? Because it will come back around at some point when it's useful.
Just the idea of if the lost we just double so much money to that that it works better than GT.
That comes now. Because we spent so much development time. But you are completely correct. In theory, a well-developed BJT will be faster, but it's a power beast. So we'll probably never care about it. At least for really tiny stuff. And we spent so much developing FETs, the FETs are really efficient at this point. So they are faster than the slightly clunkier EJPs, which we haven't spent as much money on. Yeah. So we're going to get into the design things, make things quick, but you can imagine with each of these areas, we're just covering a basic idea here. Right? There's a lot of side effects that start with so I can look at this actually becomes somewhat important to us, right? So there is this charge and discharge. So do you think there's a way we can make that charge or discharge a little quicker?
If we increase the substrate.
Okay, so I can improve the material properties, which is going to help me to achieve. Absolutely true. So material science development can improve this. What else? Think real simple, right? What's your discharge time related to?
So second,
Yeah, your capacitance. So if I wanted to go faster, what should I do to the capacitance? Okay, so how can I lower capacitance really easily?
decrease the distance between, decrease the surface area.
So I can change the distance between the plates and I can change the surface area. Okay? So are these things I can do easy?
Somewhat.
I mean, as I go smaller and smaller transistors, what happens to the area?
Very small.
So here you get smaller and smaller, which means my capacity, right? So it can hold less, so therefore it's going to get bigger. So I can alter my shape, my configuration. So I can change materials, I can change some shape, adjust the thickness of that side layer. I can change my voltage, and do all this stuff.
And I know a detailed version of this, the version between nothing completely informed is undecided, so.
So that's right.
Just one part of the chain, it will.
Yeah. So this gets to what's called pinch off. Okay. So right now we've got a channel. Okay. Now, before I do pinch off, does everybody understand how we can kind of alter it? We can tune it. You can design all kinds of new stuff. You can feed them. And again, we wanted to talk about this because exactly we just started brainstorming. You think about those directions you can go. Guess what? That's what you do in the industry. You start thinking, hey, what are they doing? What are they doing? What's the current state of it? Where do you think I can get my biggest benefits? And you start looking at it and you see, how do I adjust and tweak this? And that's what gives you the next breakthrough. Okay, let's consider these channels that are in here. And now I'm going to apply a voltage differential across here, right? So let's just say I put plus minus just for simplicity. Okay, so they're going to be going through here. And as they do, there is some resistance to this, right? Depending on how thick it is. So there's going to be a small voltage differential. And what happens to those charges? Charges go towards what? The negative goes to that positive side, right? So you're going to start seeing them wanting to move this way. So you're going to actually see a pile up as they're going to this end. It's going to get smaller. What happens if I keep increasing that voltage? It's going to eventually you're going to get to the point where there's a gap. It's becoming more and more triangular. That's potential. Right? So depending on where you look at it, we'll think the coverage layer you make will depend on how much you start with. And as you start sending something through the other side, it actually adjusts this. We'll tweak it a bit. If you do it too much, it turn it on. Right? So this is another one of those lovely little adjustment areas on how you go. Now, obviously, less voltage would be better here. There, notice that there is a trend inside of ICs where we keep trying to drop the voltage.
Because voltage regularly power plus, and we
So
want.
it reduces our power, it almost will. On this side, we'll reduce the pinch off. Now, the other side, where it's opening it increases the pinch off. So it's a bit of a trade-off there. Okay? Because the weaker you open that, the easier it is to pinch off. But the less voltage you're applying across, the less tendency to do the pinch off. So, again, another one of these lovely little trade-off areas. There's no perfect answer. Everything is a trade-off because you're an engineer, right? If it was just more of this always works better, then you could get any schmuck to do this. Right? It's the fact that there's a trade-off in here requires an intelligent person. This, this is what we call job security, right? It's the waterbed problem. It's in every single problem we face. There is no easy answer. We have to manage the difficulties. Now, in addition to that, what if I want to make this static for a second? I want to hold this. I can hold it open or whatever else. Wouldn't these charges stay here perfectly forever?
No,
Why not?
because they will get randomly excited about and bounce out on the cable. It's just the nature.
Yeah, there's going to be some that just kind of go. But also think of this, right? Is this insulator perfect?
Sorry.
Right? Yeah. The second you ask that question, perfect, your engineer's sense should go, right? Because we don't have perfect stuff available to us. So there's always going to be a little bit of a leakage current. So there's some dynamics on this plate, and you have to constantly keep replacing those. On computers, say 10 years ago, this was, maybe 5–10%. Right? The available usage of your power in the system was to handle that dynamic, the losses that we came through. On most modern machines, as we drop the voltage, that actually increases, and it's up to almost 30%. Right? So again, it's just part of that whole trade-off. So one of the things is that kind of dynamic. The biggest one is switching, where you have to discharge this to get to the other state.
It's go off.
Yes, every time you flip states, either charging or discharging a capacitor, there's just energy loss in it. Roughly speaking, you lose your energy when you charge. So you go, and it's just the limit. And so that's going to go to heat, which we got to remove. So this is why if things get too hot, we start turning things off so they can't switch. We don't even technically turn them off. We hold them where they're at. We breathe the clock to that area so it can't switch at all, because if we turned it off, they discharge. When they discharge, what would they do? They generate heat, which is sort of the thing we're trying to avoid. So in order to actually protect it, you can't technically discharge them. You gotta hold them. But all of these issues and what you have to do makes total sense because you know what's operating. So this is why I say, right, there's a general understanding of this that's essential. Because it gives you the logical thought process that lets you understand how all of these work. All right, we good? There it comes, right? You can literally spend semesters on these devices. So at this point, I'm just trying to get you to understand them and be what I would consider kind of conversant. So you understand, you can look at something, you understand what it's doing, why it's doing it, and the issues. From there, you have the basic scaffold to do anything else. All right, so we have a channel in here, and this one's channel between in the NPN, that's an N channel we want to form. From the PNP, that's a P channel. So we're going to call this NMOS, right? Because it's an N channel under our metal oxide, right? This is a P channel under that, so it's a PMOS. So this is where you get your two base, lots of different symbols for that. But essentially, we're going to do a really simple one that's just digital logic applications. We're going to use, so a capacitor looks like a plate, right? And we're going to take this, right? Here's our other line. There's our capacitor controlling it. That's an NMOS gate, right? It wants positive, so we're just going to leave it this way. Anybody remember what a bubble means?
Not.
Yeah, technically it's not. So everybody tells you it's not, but it's actually not. It actually means negative logic. It means it's a low value, not a high value. And now, when you have a low value going into something that's otherwise high value, it negates. So therefore, it in essence does something, but that's actually not where the name came from. Right? So the idea of the bubble originally was telling you negatives. And the only reason I'm emphasizing here is the pedantic points, but it explains here why we're in the bubble here. Because what do I want to open my channel here? Yeah, I need negatives. So this reminds me, it's negatives on top that are going to open that channel. So if you know what it means, it's not a negation, and it's actually, I need negatives here to make it work. So it's an easy way to remember what that symbol is. Okay, we're good with the symbols. So in essence, for PMOS, if I put ground, it's on. And if I put power, it's off. Right? Vice versa here. For the NMOS, I need power to create the channel. So power is now my on state for this one, and ground is my off state on the control leg here. So our gate. So we can't use collector emitter because we just want to change the names for some strange reason. So yeah, now we try to get something that sounds much like it meaning-wise, so we have drains and sources. Instead of a base, we call it a gate. But just realize they have similar names because really the ideas are very similar. And it just reminds you of what you're on. But functionally, they're very similar. The other fun thing is, if you remember, the PMOS is made from the PNPs, right? And in that sense, I think PNP, like the BJT, did it work equally well switching power? What was it that?
PNP was giving
It was better switching power. Right, easiest way to remember it is there's more P's. P's in this instance stands for power. So it's better than switching power. So guess what PMOS is going to be better than switching? Power. Right? Well, see, we're not putting my voltage. And you can make companies that are quite good actually at handling current on the switch side. They just don't use current to control. So when you hear about power FETs and things like that, they designed it to handle high power on that other side. But we don't care about that because we're looking at small things that we want to cover. So PMP is going to be better for power. What do you think NPN going to NMOS will be better at? It's going to be better at switching ground. So just like NPN was better at switching ground, NMOS will be better at switching ground. This is going to become important to us later. And if you're actually, like right now, you're more likely to be able to buy a PMOS or an NMOS transistor. Right, so, and you'll probably use those if you're interfacing some little microcontroller to switch a larger power source, light bulb, or whatever, turn a motor on, or whatever else we know. And remembering PMOS switches power better, so if you're switching the high voltage source, use a PMOS one. If the power source is directly wired to it and you're switching the ground to turn it on and off, you're better off with an NMOS. So if you remember these basic ideas, it'll actually help you build interfacing circuits too. So in some sense, I want you walking out of here today knowing what to do with these different devices. You'll be a much better general engineer from knowing those. Good? Awesome. Right. And it'll come to place next time. So please remember that for next time. We're going to build these transmission gate things. And transmission gates, we need people to do. All right. Now, since this is better for power, and this is better for ground, sorry, messy, right? We ideally want to be able to build a circuit that supplies ones and zeros. We're going to do this a little differently than we did with the BJTs, right? With the BJTs, we started looking, oh, how do you do things with diodes and everything else? We want to deal with that right now. Right? So what we're going to do is we don't want a lot of power flow, which means I got to get those gates with the insulators in. So all my stuff coming in, I want to flow to a gate. So I can't use that whole diode idea for most of this anyway, because I don't want things flowing. I just want to charge or discharge the gate, and then I've got this. Now, if I'm doing that, just like with BJTs, if I'm trying to use the base, I have to put power on ground. The other side I did with the pull-up. But we know you can pull up resistor. We know the pull-up resistors were not always the fastest, right? So we eventually built a total. So I had one that pulled up, one transistor pulling up, one transistor pulling down. Right? We're going to build for our first basic thing what's called static CMOS. The whole thing is going to be either pull-ups. We're only going to use transistors here. Forget the resistors that you don't slow. Okay? So we're going to have a power which will be above, which will supply all and have a ground network that's below these things, all the zeros.
You said we want to run all of one type. Is this the same thing with these, or is this where we can mix it up?
So at this point, right, I would introduce the build one of these things to be off by half a cycle, right? Because when I'm adding n for one, I'm doing p for the other. So I could just start one right, and then base for that. So it's not as the efficiency of switching using P channel to be able to switch power and the N channel to be able to switch ground is so much better. We're going to mix on the build, yeah, layers, right? Yeah, it's like nothing on the when you're doing hundreds of these stages and you're delaying it 2 or 3 before you start the other. Who really cares, right? So, and then after there's things, so it's different. So it's not that big of a delay to us, major production, and it's way more efficient. And power is what really matters to us. So you're going to basically have, right, this is the output, and I'm going to have a power network above, and I'm going to have a ground network below in our design style, right? And this is going to be NMOS, and this will be PMOS. Basically, two sides here, the power and the ground, are complements of each other because they can't be on the same. So musicians going to build this with a bunch of complementary metal schemes. You remember from because we're using E's and M's with these type of networks, and that generated the complementary part, hence the name schemes. So when you hear people talking about CMOS, it's a mixture of P's and N's, P's doing the power network and N's doing the grading network. Yay! This is really stable if you do it and don't make any short circuits. So this will be very static. So this is also sometimes called static CMOS logic. Because there are ones we can make smaller, less power, and sometimes even strangely quicker on the clock cycle by doing some other things, which we'll talk about next time. So far, so good on the basic idea. Okay, so let's do the easiest thing we can do. Imagine here's my output. I'm going to call it B. And I'm going to just hook up a single PMOS here to power, and I'm going to hook a single NMOS going to ground. And I'm just going to do, because I'm too lazy to draw the lines, I'm just going to do a triangle. Right? So I've got this basic setup that's in here, right? They're each one. I don't want this one on at the same time this one is. Well, because I put a resistor in here because I want the resistor slowing me down. So as long as I don't turn them off at the same time, they're short. So I just have to be real careful.
Pretty much the same logic gate. And we'll get this one's thing that will be on the it's all will be in ground.
So I'm going to build a logic gate right here. So this will be our first real simple gate. Right? But I'm just getting the ground volts down. We don't want a short circuit. I also don't want them both off at the same time, check. Right? Because if they're both off, what happens?
And now,
Yeah, so it's a high impedance state with C. Now, if you want a tri-state gate, that's exactly how you can do it. Turn both networks on. I'm going to float, it's a Z output, so that is what a tri-state gate wants. Right, so I can turn them all off to generate that if I want. But generally, for most logics, we're going to want a 1 or a 0. So let's get a goal, right? So we're going to have an A here. I'm going to do a real simple Carnot map. Right? There's only one variable. Right? So smallest Carnot map I can intelligently draw. And let's say I want to generate a NOT gate. So what would that look like?
A is 1, 0.
So if A is 1, and that's what's under the bar, I get a 0.
And A is 0.
So A is 0 is where A is not a 1. So that's here, so you get a 1. I'll agree that's not gate. Hopefully, Carnot maps are coming back, right? So we're going to, when you think about this, actually let me add, this is my power network, right? And this is my ground network. So I want my power network to turn on when A is 0. So what do I have to hook up to this P gate to turn it on when A is 0.
When A is 0, you hook A to it because it's ground.
Yeah, and I want a 0. So, there we go. I hooked it up. I have now supplied the 1. I have no 0 here. Nothing at the moment is happening in this case because this gate only turns on when A is 0. When it's 1, that gate's on. Right? I now want to supply my ground. So I now think about this one, my ground network. I want this to turn on when A is true. Right? Because A is true, I want ground network connected. I hooked it to A. See why I'm getting the comfort with this? Guess what you just built? Okay. This is stupidly easy, particularly if you think of it in terms of just build it with the lovely Carnet apps. Right? So this is interesting as I can make it one here, one controller here. So let's go with 2. Okay? All right. So let's say this one we kind of built them on. Let me take a look at something a little more interesting. What if I have something that looks like this? Here's my output C. And I'm asking, I say this correctly implements my power network. I want you to figure out what it is and see what my grid network should be. Make sense as a question? Okay, so our first step should be what? I want to figure out what the power is. So how can I figure that out?
So when A is 0, it's on, and so when B is 0, it's on, and so the only way the power flows is if they're both on.
Okay, so both these have to be on.
I'm going to assume this is an AND gate that we're building. And
That's some variety, right? So the thing you see two in series, there's some AND-like function. Now, it doesn't necessarily, you don't necessarily know off the bat, right? Because I could have primes on whatever. But it's going to tell you that it's going to be at that intersection of those two variables. So I should draw a Carnot map as my first step for this one. Oops, I should give myself a little more room. All right. All right. So now we know when A is 0 and B is 0, I get a 1. We agree? So where my Carnot map is A is 0 and B is 0. Yeah. Right? Because this is A is 1 column, A is 0 column. This row is B is 1, B is 0. So this is where A and B are both 0, so I get a 1 there. That is my Bower network. Right? So where do I want my ground network? Just take a look. I don't want it short, and I don't want any Z's. So where should I put the zeros? Everywhere else. Don't overthink it. It really is as easy as that. All right? Now, think about encirclements. How am I supposed to encircle things when I do Carnot maps? Anybody remember the basic rules? Has to be powers of 2. Very good. All right? So, for instance, in this case, I got 3, so I'm going to have to do them 2 at a time. I also want the biggest one I can do. Can I do this? Why not? So, is there
You can do that on the blue.
it's an XOR. And so diagonals are XORs or XORs. So the reason why we do diagonals is XORs and XORs are pain in the butt circuit. They're slow, they're big, they're clunky, they consume power. That's why we don't like them. Okay? but it doesn't mean it's impossible. So in basic digital logic, we tell you don't ever do that, right? And we verge on the it's impossible. But the reality is that's an oversimplification to keep you from doing something dangerous, slow, and expensive. Uh, The reality is it's not impossible, it's just really dumb. Okay, so you're gonna have a good reason for it. But diagonals, yeah.
In Explorers and Explorers, does that mean?
They're at least 50% longer than comparable bands or norms. So that's why I mean I'm slow.
Right, so does that mean it's better, like in my practice, is it better or worse in the case of cryptography? Because the cryptography is just all the experts.
It is, right? But if I were to build cryptography, it's really hard to do that with just a single other gate type. XORs have a neat property. For some of the properties of cryptography from number theory, you have to have an equal number of zeros and ones.
Right.
That's an underlying assumption of math, because otherwise you have to skew that distribution and necessary. Right? So now you have to have equal numbers. So that takes out AND and NOR as a simple layer. Right? If you did 2 layers of AND and NOR, it's going to take twice as long as 1 layer. So the XOR that's 50% longer than a single NAND gate
Versus all versus all.
versus 100% slower is a better deal. Right? So since it is what is mathematically required, I can't avoid it. So again, when I'm saying it's bad, it's slow, it's all that. So it's bad to do with the caveat, unless you got no choice. And if you're doing cryptography, there's actually several related ones to cryptography. It just has the machine you can do. Error correction falls into the same category. It's easier with XORs. It's just mathematically required. Now you got no choice. So now you have really solid reason to jump to that XOR because it's the only game in town. So it is better than the alternative. Right? But you don't want to build circuits out of it, because imagine 2 layers of this. Okay? It'd just be bad. Okay? Does it make sense to people? So it is a very good question. All right. So I want those zeros there, so I have to do encirclements that are going to be rectangles, powers of 2, and they have to be aligned horizontally. Make sense? So in this case, I'm going to look at this and this. Okay. So what is this vertical one?
If A
This is,
not true.
so I want a 0 when A is true. That's the simplest thing, right? Because remember, there's different rules when you get into whether you're using NANDs or NORs, right? Whether you're doing sum of products or product of sum encirclements, right? There's some variations. We're not even going to worry about those rules because you don't even have it. We're just talking gates turning. So I'm just using this as a simple way to write those down. So I want a 0 when A is true. How do I do that? And how do I hook an NMOS data to do that?
If you, when A is true, it's 0, that means you need to hook it directly to A and A.
So I just hook to A. Exactly right. So, yeah, that's green. I want to stick. Where's my black one? There it is. Okay. So I want an NMOS that's hooked to A. Now, this encirclement, is it dependent or independent of the other encirclement? It's completely independent. So these are parallel lines. So here we go. That's one line. That's that encirclement. How about the second encirclement? So now I also want another one that's hooked up to B.
Just connect the one NMOS to
Could I not just, I'm not sure what you're,
so you got to split the gate wire to A and B. So it's a A and 2. You just use one and just split it.
Yeah. So I'm not sure where you want me to
At the gate of where A is, could you not just say split that and put that to B instead of using more in-laws?
oh, you mean have A and B connect to this? Right? But then you don't actually put some protection to prevent what if A and B are the changes. Right? So potentially you could shop back at whoever's sending this to you. So building the second one here just allows me to completely electrically isolate them. Now, could you, now, is squash the idea? Because what if I made two independent little ones that had two channels on the same transistor that were just independent? So in kind of like 3D, I have a single transistor. Let's see if I can do a fairly decent 3D type thing, right? And so imagine that I've got my N, P, and I've got a layer of oxide here. And I have two different kind of capacitors on top. Fine. So I'm kind of making a 3D look at this. I could, they're now independent. I could hook one to A and I could hook one to B. Yeah. And you can make different channels. Fine. But in essence, it's the same as building two of these. Yeah. I've just made it a little more efficient on how you combine them. So logically, it's the same thing. You just made it a little smaller and a little more efficient. Right? So that still fits within this general area. That's kind of like, can you make a bigger transistor implementation of this? I think, what would happen if I took these same things and twisted them sideways? Is it, so this is actually important. You're switching that way, and you have to have both of them on the full channel between the two sides. So, in essence, I've got that this bulk out kind of orienting them this way. Right? So the word is you can kind of squeeze these together in different cute and creative ways. Right? Doesn't seem to be making sense. Imagine that one I can draw easier. Right? Imagine I had again an NPN, but I made it, here's your insulator, and I made two separate gates on it, one hooked to A and one hooked to B. And I put insulator between them or whatever, right? So it's thin. Right? A would control the formation of the channel here, and B would control the formation of the channel. The only way you can get full channel also has to be activated. So my opinion, and it's a good point you make, right? This is why I say keep a gentle feel on it, because then you can start thinking, how can I create it? How can I make this smaller? How can I do what the efficiency of it? This becomes interesting questions, right? So you can make smaller, better, stuff. Okay, good. So this right here, what did you just build? Yeah, you built that. Two.
And gate is split.
So what you can navigate, right? So notice that one, I could give you half a network and you can show me the other half. That's what we also kind of proved from that one. But let's start off and let's now say we want a NAND gate. Right? So what's a NAND gate look like? Right? So I want a zero there and ones everywhere else. That's not NAND. And is true when you're both. This one's false. Okay. So now we're going to do our networks. What do we want to start with? Power or ground? Power? Awesome. Let's see. Red pen. Awesome. So I do my encirclements. 1, 2. So let's do our power law. Let's do, for instance, I don't know, how about this one first, right? This vertical column. What is that one? Okay, so for this one, I want, when A is a 0, I want to supply power. How do we do that? It's a PMOS.
It's uh, you want that's on.
Right? So, yeah, I want to supply power when A is low. How does a PMOS gate, when is it on? When the gate is low. So that's ready-made in heaven for me, right? If I hook A to that, when A is low, it will turn the gate on. Right? Are these two gates that I did encirclements on, are they independent of each other or dependent on each other? They're independent, so I can hook this right to power. All right? How about the second one? This lovely one across the top. Same thing except for B, right? Because when B is low, I want it on. And when you supply load to the gate, it will open. So I just need another one coming from here. Anybody can want to take a guess what the ground network's going to look like without even thinking about this?
So stack.
Yes. So if you notice, when they're in series, on the other side there, right? Here they're in parallel. You would expect they're probably going to be in series. It's the complement, right? Again, that fits in a nice complementary area. That's if you encircle it, you'll notice it is both A and B have to be one. So that means I do indeed have to hook them in series so that both go to ground. And I want them when they're both on to open. Well, that's exactly what it does if I just hook A and B. Yeah, we just got the two universal gates. So you have built your first little CMOS NAND and OR gate.
Which separate.
Yeah, now you can build whatever you want. Right? Realize I could do this crazy big if I wanted, right? I mean, if I wanted to go in and let's just take a ridiculous extent to this. We got like a couple minutes. What if I did A, B, C? And let's say whatever I want, ones here and zeros everywhere else. So I got ones, I got zeros. What are my encirclements on the ones? Let's do our power network.
B is B is all and A is all.
Yep.
And B is B is all.
No, the next one doesn't.
A is all.
And C is on. Okay. Now let's build it. And then we'll do the ground network. So I've got two independent ones, so I know I have two lines. But each of these involve two variables. All right, so I know, right, since each encirclement is going to be two variables, I'm looking at this. Let's do this one, right? I need A to be 0 and B to be 0 to get a 1. Well, that means I need A and B here. Because when they're both 0, it'll be low, turn those gates on. When both are true, out things flow. Agreed? Can somebody help me with the other network in the power?
A is so A, C.
Now, anybody notice anything funny here?
Is that 2A's?
2A's. Could I do this better?
Yes, you just put them obviously 2A.
Yeah, so I can actually just get rid of that one and hook it across. Right? Let's see if it is. A little more efficient. I got one gate. Okay, so awesome. What's my encirclements for my ground network?
A's one,
And
B, and C.
yeah. Now, notice this one right here, right, is going to just, in essence, only require A. There it is.
So, show 1A, so one here,
One gate going to ground, right?
B.
When A is true, it will turn on. Now notice, by my efficiency step, remember, what is in parallel ends up going to series and so on. And here, A was in parallel to whatever this other thing is, and A is in series with this here. See how that series to parallel flip works perfectly? Be more obvious. Let's draw the second half of this and it'll hopefully even make more sense.
C,
The second one has 2. And what's the requirement for this one?
C, A.
Yeah. Right? So I need both B and C to be true, which means it's B and C. So notice I've got up here, A is in series with B, C in parallel. And on the bottom, I have A in parallel with B, C in series. See how they just flipped? That is not an accident. Right? Remember, all this logic now, we're saying they're going to be complements to each other. And really, all I'm doing is exactly getting that complement. So you have all that token stuff still working on. So yeah, they're going to fit nicely. Now it's just parallel and series is actually operations that fit. Okay? So you can actually even see the efficiency of containing the 2A gates. If I didn't do it, I would have ended up with 2A gates in series and then all that. We're out of time. Does that make sense? How we can make static gates? This is the basic, right? This is the most typical ones. We'll talk about faster and better and all kinds of other potentially stuff next time. All right. Have a lovely day. Just as a note, I did expand the my notes a little bit. People were mentioning that there wasn't much in the BJT thing, so I wrote down some of the stuff for BJTs and uploaded it. And I fixed a couple other things too, but mainly the BJT ads.